Today we're going to talk about enthalpy and how we can calculate delta H for a chemical reaction using calorimetry. But before we get into calorimetry, I do want to make sure you guys understand some things about enthalpy. First off, enthalpy is an extensive property. And remember, when we talk about it being an extensive property, it quite simply means that it depends on the amount. So if I have 5 grams of a substance and that 5 grams is able to generate 10 joules of energy, if I take 50 grams of that substance, I'm then going to be able to generate 100 joules. And so it depends on how much we start with. The second thing is that the forward process of a given chemical reaction is endothermic, then the reverse process will be exothermic. The magnitude of the change will be the same. And so if we look at these two chemical reactions, right, so if we start over here on this side and we look at the synthesis of H2O, then we know that delta H for this process is going to be equal to a negative sign because it is an exothermic process. So if we look over here, down here at the energy diagram, we can see that delta H for this is going to be equal to a negative 484 kilojoules. Now, on the reverse side of that, I lost my arrow. If we look at the decomposition of water, when we have the decomposition of water, this will actually be an endothermic process. So we just flip that. We're looking at the reverse process. And again, that should make sense. And in this case here, if we're looking at that magnitude, delta H is positive, it's endothermic, but we're still going to be at 484 because the same bonds have to be broken, the same bonds have to be formed, but we're just doing it in a different direction. And then finally, we see that enthalpy is a state function, and that's going to be important for us to remember. So what that means is that the enthalpy change for the reaction is going to depend on the state of the reactants and the products. So when we start writing chemical reactions, you're really going to have to pay attention to what state they're in. So for instance, if we look at the first chemical reaction, we have the synthesis of water, it's in the gaseous state, and delta H for this, as we said up top, is going to be 484 kilojoules. But now, on the second one, we still have the synthesis of water, but now it's in the liquid state. And so we're going from the gas to a liquid, and in this case here, this is 572 kilojoules of energy would get released. And we see that's a pretty big difference. Well, the reason why is to keep something in the gaseous state takes more energy. And so if we want to go from the gaseous state back to the liquid state, then we need more energy to get released. And so we see that, and if we take it all the way down to the liquid state, to be able to form those bonds, we need to release more energy. And so that's why it's a state function, and we have to pay attention to what state these things are in. All right, so let's get into this calorimetry business and talk about how we can use calorimetry to calculate delta H for a given chemical reaction. So there, like you guys read about, there are two different types of calorimeter. The first one is a coffee cup calorimeter, which is a really simple setup, one that we're going to use in most high schools, and then we can also have a bomb calorimeter. And so there are two, the one main difference about the two is that if you're using a coffee cup calorimeter, the reaction must occur in solution. Right? And so whatever chemical reaction we're doing, it has to happen in solution. And when it happens in solution, we're looking at basically recording to know what happens to that energy, whether it's taking in or taking off. We're looking at recording the temperature of the water here, right? And so if we look at the temperature of the water and the temperature of the water goes up, right, what we can see is like, ooh, it's gaining water. And so if the temperature goes up, delta H will give negative because that means that it's exothermic. So anytime that we see an increase in the temperature change, then it's going to be an exothermic process. If the temperature should happen to go down, then obviously delta H would be positive. So in this case here, temp goes up, delta H is negative, temp goes down, delta H is positive. And that's the thing that we have to pay attention to. So let's look how we apply this to a problem, right? I'm not going to read the problem to save some time. You guys can read through it. But again, we have some HCl and some NaOH that we're going to mix together. If we want to, we can write a chemical reaction where we have HCl plus NaOH, and that's going to give us our NaCl plus H2O. Now, for this one, fortunately, we don't really need that, but it's good to have that balanced equation there. Now, anytime that we're working with a coffee cup calorimeter, we're always going to use the same equation, that equation of Q equals MC delta T. This should look familiar to you, where Q is going to be heat energy, right, measured in joules. M is going to be equal to the mass of solution. Remember, that's solvent plus solute. C is the specific heat of the solvent. Most of the time, it's going to be water, and so that makes it a lot easier for us. And this is going to be joules per gram degrees C. And then actually we have delta T, and we all know that delta T is equal to the change in temp. So let's look at how we can use this to go from this information to get us to delta H. And so we have this, we mix these two things together, and we see that the temperature here goes from 21 to 27.5. So automatically by the end, we know delta H is exothermic. That temperature increase, heat was being released, and when the heat gets released, we heat up the water. Delta H has to be exothermic, so we know that already. So let's see how we can get the value of delta H. And so we know that Q here, in this case here, we're mixing together 50 milliliters and 50 milliliters. That's going to be 100 milliliters, right? And since the density is 1, we know that that then equals 100 grams of our solution. So we have 100 grams of solution. We know the specific heat of, in this case, we're going to use the specific heat of water. That's 4.18 if you don't remember that. And then we have the change in temperature, which in this case is 6.5. Now, so in this case, we have Q going to be equal to, what is it equal? 2717 joules. Now, that's how much we have, but we see from the problem up here, we wanted that to be in kilojoules per mole of NaOH. And so what we have to do is know how many moles of NaOH we actually put into the system. And so we get that information from the top. Here again, we put in 50 milliliters of a 1 molar solution. Oh, I forgot to put that in this problem. That would probably be helpful. So that's a 1 molar solution. And so we have 0.05 liters times my 1.0 mole for every 1 liter, and that's going to be 0.05 moles. So now, since we know that, we have our Q, and so our Q, we can say, well, Q is going to be equal to 2717, divide that by 0.05, and that gives us our 54,340 joules per mole. But we want to convert this into kilojoules, and that's going to be 54.3 kilojoules per mole. And so since we know that delta H is negative because our temperature went up, our final answer would be delta H would be equal to a negative 54.3 kilojoules per mole. There you have it. So now, not all chemical reactions take place in solution, and we know that. And so while coffee cup calorimeters are pretty good, even though they're really basic, they only limit us to doing reactions in solution. So if we had enough money and we could pay for it, then we could use a bomb calorimeter. The big thing about bomb calorimeters is it allows us to work with dry reactants. And so we can see that it has a little reaction container that's separated out from the water, so we can work with dry reactants here. Now, most of the chemical reactions that they work with in a bomb calorimeter are going to be combustion reactions. It's the most common type of reaction to do in a bomb calorimeter, because you can fill the tank with oxygen and the substance that you want to. You have these ignition wires, so you can supply that activation energy and you can get it to go. And since we have a combustion reaction, we know most combustion reactions are exothermic, so that heat kind of comes out here and goes out, and it just heats up that calorimeter. And so here we see again, right, we're expecting the temperature in that calorimeter to rise, and because it's a combustion reaction. And so most of the time when we have these things, delta H is going to be negative. But again, to make sure, we can always check the temperature change. Now, what we do for this is going to be a little bit different, how we calculate it, because most of the time what we're going to see for a bomb calorimeter is that we're going to be able to find what's known as the heat capacity for that calorimeter. And the heat capacity is measured most of the time in kilojoules per degree C. And basically what that means is, for this entire setup, what we're measuring is how much energy it took to increase the temperature of the entire setup by a degree C. And so that's what the heat capacity. We're not just dealing with the water, we're dealing with the metal in there and all the other stuff. So we're just looking at that heat capacity. And so if we look at our problem here, our sample problem, we're combusting our C2H5OH in our bomb calorimeter. We're not going to worry about setting up that balanced equation. But right now we're going to look at, okay, how do we do this? We have a certain mass of the substance. We have a heat capacity of our calorimeter. We have a temperature change, and we see the temperature increases. So we know automatically that delta H for this process is going to be negative. And so now it's asking us to calculate the heat of combustion. The heat of combustion is just basically a fancy word, as we have a combustion reaction. What's delta H for it? So don't get hung up on that terminology. So the question is how we do it. Well, the formula is slightly different. We're still going to find Q, which is that heat energy. Then we're going to use that. To do that, we're going to use capital C CAL. And this is the heat capacity. We're going to take that heat capacity and times it by the change in temperature. So really simple two steps. And so in this case, we'd have Q. We're going to take that Q and we're going to multiply that Q by the 4.62, and the change in temperature in this case is 4.94. And so the Q for this is going to be equal to 22.82 kilojoules, right? So because we see the heat capacities in kilojoules per mole. But now they want it in terms of kilojoules per mole of the substance. So now we just have to do one more step where we have our 0.7971 grams of our C2H5OH. We're going to divide it by its molar mass. So we know that for every 1 mole, we have 46.08 grams, and that's going to give us 0.01730 moles. And once we have that, then we can take our heat energy, divide it by our 0.01730 moles, and that's going to give me 22 point, oops, I lied, wrong number. That's going to give me 1391 kilojoules per mole. But again, since the temperature, oh, that was kind of weird. Since the temperature went up, we determined that the reaction is exothermic. So now delta H we know is negative because the temperature went up, and that's going to be our 1319 kilojoules per mole. And that would be our delta H, or the heat of combustion for this particular substance. Okay, so what I need you guys to do is work those book problems that I have assigned in the topic page, and then answer the the daily task, and we'll go from there. I will post problems or some write-ups for these problems tomorrow, some videos of how to solve those book problems tomorrow in this topics page. So make sure you check those out if you have any questions. All right, y'all. Peace, love, happiness. Thanks for playing.